Hey everyone, how are we doing? I see we got some questions from Ahood in the chat, and we got some questions, I think it's Trace in the chat. So hopping on here, just had a quick meeting, getting a lot of things ready going. Awesome news, especially with the Discord. So every time we talk about lag, I have to stop and think about this word again because I did not understand what it means. So we saw some good stuff today, especially in the end of 475 with lag. Let's go look at it. And we were talking about the neural nets today and the way the lags look. So let's go and look at the neural net lag on this, which are the inputs for the neural nets. And just to see is, hey, Cliff, what's happening? Good to see you here, Cliff. And here we go. Let's take a look at what lag actually looks like here on the screen. So I think this might communicate better what a lagged variable is. If we're talking about lag, we're talking about a previous period and how that previous period explains it. So what do you notice here at lag 1? The value right here at time 2, lag 1, is the what value. So when you look at this just visually, at lag 1, time 2, we're just going through a time series. This is time 1, time 2, so we could just put it right here, time. Just at time 2, lag 1, the value is what right here? That's the lag 1. This is time 2. I sent you up on Discord. It's a neural net. Oh my gosh, Ben, that's awesome. I will check that out immediately when I get back today. I'm really excited. I was hoping, did you put some tuning parameters on the neural net? I'm really hoping you did, because next semester I think I might have people do that. Like, you have to have a page with the neural net with the tuning parameters. Because I was thinking about that as I was grabbing my coffee between classes. I don't have coffee anymore. But what do you notice right here about these lags? Like, look at the value right here for time 2, lag 1. And then why do we not have lag 2 at time 2? Why do we not have lag 3 at time 2? Why do we not have lag 4 at time 2? What? What's going on right here? What are these lags being created from? You have to see it. I can say the answer, but you have to see it. And you have to be like, wait, this value right here, when it's lagged, like if we go to time 3, lag 2, then what are we getting here with time at time 3? So this is the value at time 3. Like this is the actual value right here. So we could just call this y for the actual value. And since we have the actual value of y right there, the actual value, but then we have its lagged value right here. So because there is no lag for 2, pretty much, I think you're saying like at time 3, there is no lag 3 because you would have to go back 3 periods. I made a reactive dropdown that lets you put in the number of periods before. Yes, Ben, awesome work right there. Is this making sense, Ahood, right here? Does it help to visually see this? That when you are looking at the lags, to get the lag 2 at time 3, you would go back here and go back 2 periods. To get the lag 1 at time 3, it would be the value in here. But to get the lag 3, you would go back 1, 2, and you can't go back 3 periods because the time series doesn't go back that far, so it's missing, hence NA. To get the lag 4, you would have to go back 1, 2, 3, can't go back 3, can't go back 4. So once again, hence at time 3, there is no lag 4 value. We can't go back 4 lagged periods because this doesn't exist. And this is how we can build our autoregressive models and our neural nets, by using lagged values, by going back in time and then creating weights for these. Phi with the autoregressive model, and the neural net's going to do a little bit similar. It's going to throw in some randomness. But I think seeing this structure right here, that if you were to look at this value right here, this value is going to be 4 periods backwards. So let's go ahead and code this box. And we're talking about this period right here. So if you go back 1, 2, 3, 4, boom, there you go right there. So hopefully seeing that this value here at lag 4, and because we're dealing with quarterly data, this is going to account for the seasonality of the data. And the good news is where we ended class today, is where we made a neural net that accounted for this. And this was our neural net that did not account for seasonality. And then this was our neural net that did account for seasonality. So when we used a lag 4, which are going to be the inputs to the neural net, this was the lag 2, I believe. And then we switched over here to a lag 4, and we really see a lot better on the seasonality. I mean, these predictions are super awesome. I might be worried about some overfitting. I don't know. We really need some more test data. I want to find the answers to the Johnson & Johnson further out. We really need a better holdout on this. We didn't use a holdout. And we talked about those concerns at the very, very end of class about the way in which we're doing this model. I will post these notes later. The way in which we're creating the model creation is happening right here with the creation of the lagged variables. We're creating a data set with the lagged variables. This is where I was just writing my CSV file to look at. And then we're training the model right here, hence 474 crossover if you're in 474 today. And then we're using method neural net, the line out, the trace, which is going to control the output. And then we have our predictions being saved. And then we calculated the root mean square error, which was extremely small. Smallest root mean square error we've seen, but I am worried about overfitting, which means 474 and 475, both of you now, means I'm worried about will it work on new data. And then we have a question about 1F. Trace has got a question here. Let's go back to the main screen. Time for another question. Can you go over 1F part 2 for 474? I still understand the numbers. And this is the Britney Spears and the like more likely by random chance part, I think. And so let's talk about this right here. Where is the assignment? I think this is it. Is this a blank copy? We'll find out. So going down here, I'll have it up in 1 second on the screen. A, B, C, D, E, F. Here we go. Let's go take a look at another question on the main screen. So the lift of this rule right here, who can explain what the lift means? So the lift of Hillary Duff, Rihanna, Ashley Tisdale is about 7.2. The lift of Hillary Duff, Rihanna, Ashley Tisdale is 7.2. By commenting on how often these bands appear together in a user's list of likes compared to lists generated when users pick them at random. So we need to comment on this lift. We need to comment on the lift by talking about it, how often these bands appear together in the actual list than we would expect via random chance. And this actually goes to, I'm going to bring up some of the notes for this. So 2 seconds right here. I can bring it up over here on this screen. So let me go bring up the notes and show you what we're talking about. It goes to the equations. So the equations we're using, let's go bring up the notes, association rules, mega notes. And let's just download them right here. And let's open them. Okay. So let's go into, no, actually further back. Here it is right here. So let's go ahead and take the equation. Now this goes back a little bit. Lambda auto. Yeah, you can just lambda auto. I don't think it does. I think it does null or it sets to 1 by default, which means it's not going to use a lambda. Double check the default, but I think it uses, it doesn't do a lambda transformation unless you ask it to. I think it doesn't do a lambda transformation unless you ask it to. Let's look at this right here. This equation right here is the top part. When Hillary, Duff, and Rihanna are in the antecedent, Ashley Tisdale is found 72 more than expected by random chance. Correct. And I believe that is the second way. I believe that sounds like the second way we would interpret it. The bottom part of this equation right here is if you think about the event A, which is having in your playlist Hillary Duff and Rihanna. So let's put H and R. Having these two in your playlist. And let me see here. No, I think this is the first way. So yeah, because the second way is the given way. I think you have this correct. And then this right here is going to be Ashley Tisdale. Let's put A for Ashley. This is the probability by random chance. This is the random chance probability because we're just using stat1 methods. When you multiply two things together, you're just seeing mathematically the random chance probability that A and B would occur. Does that make sense? Hillary Duff and Rihanna and Ashley Tisdale appear together in the list 7.2 times more frequently than we would expect by random chance. And that's what this bottom portion is right here. That's what the last thing you're saying is. And then this ratio right here, I think Ben and Trace are on, that's going to be full credit right there. Up here is what we observe. This is the actual union. Make sure I get, yep, I think so. Automatically does box cuts. It does nothing. Awesome. Thank you there, Timothy, right there. Seeing how that works. Definitely, sorry, might have got that wrong. Automatically does box cox lambda. And it does nothing if null. So put in null if you don't want the box cox lambda. So the intersection for and. That always gets me. That always gets me. And this is where we see right here the overlap. So that's the intersection. Thank you, Trace, right there. That's what we're talking right there. Just words, math words always get me. Trace, 50 points. Please correct me if I say something wrong. So that's what we're talking about right here is when do A and B occur at the same time. So this is what we observe up top. And then this is what we would expect via random chance. And what we're saying right here is that this value of lift, when we solve this, is 7.1. And by the value of lift being 7.1, think about what we're saying. We observe 7.1 times more, as in it is observed 7 times 1 more that Ashley Tisdale appears in lists with Rihanna and Hilary Duff than we would have expected by random chance. Write down here this mathematical computation. So our observed percent of time seeing Ashley Tisdale with Rihanna and Hilary Duff is 7 times 1 more than we would have expected via random chance. And this is just classic mathematical computation. And what do we assume when you multiply two things together in mathematics? 201. We assume that they are randomly, like there's no association between them. They're random. So the calculation right there, A times B, the probability of A times probability of B, is going to get you the probability of them appearing randomly together. But then we actually look at the intersection, good mathematical words to know, the intersection between the two, which is going to be how often do they actually occur, which is they're observed. Does that make more sense, Trace and Ben, seeing this right here? We're just resolving this equation to kind of more statistical words to saying this is how often we observe them together. This is how often we would expect them to be by random chance. And the ratio of these two numbers means that we observe them together, these three items together, 7.1 times more than we would have expected via random chance. These can be any sort of numbers when you're solving it. Like for all intents and purposes, we could observe them by random chance, not saying these are the numbers, 10% of the time. And then we could observe them together 71% of the time, and this would make a lift of 71. So by random chance, we would expect to see them together 10% of the time, but we actually observe them together 71% of the time. Anytime, Elizabeth, we got it. Open floor after this one. You got it. Elizabeth, throw in a 201 question. I'm going to the dentist here in just a little bit, but definitely for part 2, how do you get the probabilities? I try and run subset to get the rules, but it never works. We'll take a look at that. Elizabeth, put a question in the chat. We'll do it next. Thank you, Elizabeth. And this is a little 201 right here because we're just multiplying the bottom to do the random chance probabilities. Elizabeth, thank you for swinging by. Throw a question in the chat, and we will do it next. And by calculating and commenting on the probabilities of finding Ashley Tisdale before and after knowing they're in the list is in the list list of likes. Yeah. This interpretation requires using the value of lift and the support of Ashley Tisdale. Okay, how can we find the support of Ashley Tisdale? What can I go to? Hint, there's the first letter. What can I go to find the support of Ashley Tisdale? What can I go to find the support of Ashley Tisdale? What can I go to find this first letter right there? Item frequency. Let's go to the item frequency, which will tell us how frequently things appear. I believe this is called music. We're going to go here and just search for Ashley Tisdale, and we can find the support of Ashley Tisdale between when to reject and when to fail to reject. Yes. Let's do a sample problem on that next. You bet, asked Elizabeth right there. So this means right here, 8.95% of playlists have Ashley Tisdale in it. What does the lift mean, though? What does the lift mean? So what does the lift mean right here? So if we have the lift, then that means we would take this. And what do we have right here? Just think about, this is the answer to the question. This is the probability of Ashley Tisdale right now. Just randomly someone having Ashley Tisdale in their playlist. Like, do you have Ashley Tisdale? Random person, about 9% of the time. But with the knowledge, this is like posterior before knowing, or prior, before knowing they have Rihanna and Hillary Duff. But now if we know they have Rihanna and Hillary Duff, the probability increases by a factor of 7.1. The first one kind of deals with mathematical ways of talking about it, like the probability of them being together by random chance versus what we observe, showed that equation. But this one right here goes with a prior, before, just like random person on the street, 9% probability of having Ashley Tisdale probably in about 2010 or so. But then given you have the knowledge that they have in their playlist, Rihanna and Hillary Duff, they would now be 7.1 times more likely to have Ashley Tisdale in their list. And we have now calculated the what right here. This, last question on this, and we'll do some 201. We have now shown that this is the what for them having Ashley Tisdale, given they have Hillary Duff and Rihanna. So this is the what for Ashley Tisdale, given they have Rihanna and Hillary Duff. So this right here was the support of Ashley Tisdale. This is the lift in the rule. And this is the what in the rule. Because this is kind of how what we are, that they'll have Ashley Tisdale, given they have Rihanna and Hillary Duff. So we're basically writing it out right here like we have Rihanna, Hillary Duff, and we're asking the rule of Ashley Tisdale, the confidence. This is the confidence in the rule. Given somebody has Rihanna and Hillary Duff, then what is the probability that they'll have Ashley Tisdale? This right here is the original support of someone having Ashley Tisdale. Like, without any knowledge, 9% of people have Ashley Tisdale. But with the knowledge that they have Rihanna and Hillary Duff, then it increases by a factor of 7.1, which is the lift, to the new probability of 63.6%. Is this making sense right here, especially with this interpretation? By calculating and commenting on the probabilities of finding Ashley Tisdale before knowing, this is before knowing, and then knowing if it's in the list, we can use the lift right there and explain how before knowing any information about 9% of people, after knowing this information, it increases by a factor of 7.1, which is the lift. And so we get kind of what's called a posterior probability, which is like after we know something. Prior to any knowledge, we have this probability, and post knowledge, we have this. Is this making more sense, Trace, Aaron, and Ben? Great questions right here. A little connection to Stat 201. A lot of the topics connect. I think it's got it. Puppet Shark, do you understand it? Yeah. Man, he knows everything. Let's go back to the main screen and do some 201. I like to say a lot of what we do boils back to 201. Very important class, lots of great knowledge. Let's go do a little null and alternative hypothesis. I'm going to pull up a 201 question from the homework. We'll see how much time we have. Going to go to the dentist here in a little bit. Thank you everyone for swinging by. If I don't get to your question today, since we're doing slightly shorter office hours, and I'm probably going to move office hours tomorrow to after a meeting. Friday is like meetings day. We are getting a 201 question up and going as we speak. So let's hop down here. Let's do one that's due tonight or tomorrow. Do tomorrow. Let's go do a quiz question. Replace questions. Okay, let's do a quiz question that has nulls and alternatives. Okay. So here we are with the first 201 question. I think we got time for a little bit. Let's practice. Now, whenever we write nulls and alternatives, here's a really quick trick you should know. 201, 320, 474, 475, you should all know this. The null always has the what sign. The null always has the what sign. Adam, good to see you here. The null always has the what sign. What sign does the null always have? I repeat this all the time. The null has the what? If we're writing a null hypothesis, the null has the equal sign. Great job, Elizabeth, right there. It also has that HO standing for null hypothesis. So what do they want to test right here? Casino wants to know if their slot machines really are paying out 3 out of 100 times. So we have to ask ourselves, Is the machine paying out yes or no? Which means this is a what kind of question. Is the machine paying out yes or no? So is the machine paying out yes or no, making it a what kind of question? I'd mentioned the 7.1 also. Basically, I'd throw in the 7.1 and I'd add the decimals since we're doing a written answer. Throw in the 7.1 and put in the decimals. That's what I would say to just make sure the grader doesn't get mad. You can always dispute a grade too. You guys be like, I think the grader was too mean, Brian. And I'll be like, let me look. So since it's does the machine pay out, it's a what kind of question we're dealing with. Does the machine pay out? Not how much does the machine pay out, but does the machine pay out? Two types of variables, categorical, quantitative, and we're asking, does the machine pay out? Does the machine pay out? We're not asking how much does the machine pay out, which would be quantitative. So we're asking a what kind of question by does the machine pay out? So by asking does it pay out, it's a is it C or Q? Hey, good to see you. Bulgarian friend in the chat, good to see you. Doing a little 201. We were doing some time series earlier. Since we're asking does it pay out, we are doing a great job, Elizabeth Rayer, categorical. Now, we want to know the truth. That's the summary proportion or the sample proportion. That's the true proportion. That's the sample mean. That's for quantitative. That's the true mean if we were doing quantitative data. We're doing categorical and we want to know the true proportion of times the machine pays out. So P goes with proportion, kind of easy way to remember. And the hat means estimate. We're not trying to understand the sample proportion. We understand the true proportion. So we're going to put down here P for all of these, nice and easy. And what are we asking? We're asking if P is equal to 3%, which means, is it true that the machine pays out 3% of the time? Or does it not pay out 3% of the time? The next question says, last year customers spent this amount. Sounds like we're dealing with not categorical anymore, but quantitative. And that's where we analyze the true mean. So mu is the true mean. And then we're going to analyze quantitative data, which means we're analyzing the mean. Like you're averaging things together. You have to have like 10, 20, 25 to average things together. So now we go down here and we put the same symbol for the null and for the alternative. And then the null always has, we said it earlier, we said the equal sign. The null has the equal sign, and then we have to look at the alternative right here to see which way it goes. Last year, customers spent about $50 per visit to the company's website. Based on a random sample purchase this year, the company wants to know if the mean this year has decreased. That is their question, and they're asking, has the mean decreased? And just look at this right here. Has the mean decreased? Great job, Elizabeth. Another 20 points in the chat. Yep. And this is just practicing writing the nulls and alternatives with signs, which is a great place to start. A pharmaceutical company wants to wonder if their new drug has a cure rate that is lower than, look at that, we're already finding out the alternative. And we're asking, are people cured? So if we ask, are people cured? Then we're asking yes, no. Just always break the question down to, are people being cured? Well, then we'd be saying they are cured, yes. They are cured, no. Categorical, amazing work. This is the practice, because now we've got a lot of answers to a lot of these blanks. It's a lot of blanks till you realize the null has the equal sign. We'll just throw that in right here. And then the first part is going to be categorical quantitative. A bank wants to know the percentage of customers who are using their website. Now be very careful. Percent sounds quantitative, but we're asking, is somebody using our website or are they not using our website? I think so. We might not have enough time, Cliff. We'll double check. And I can answer on Discord too, because I'm going to have to run here for the teeth. So we're asking, is somebody using the website, yes or no? So we're asking, is somebody using the website? You might say, well, it says percent, and that's like a number. But the question is, are people using the website? And has this number decreased from what it was? And this is the null amount. So once again, this is proportions because we're asking, are you using the website? It's like how you would phrase the question. Like to each customer, it's, are you using the website? And from that, we'll get the proportion of people, which could be a percent, but that'll be obtained by asking, did you use the website? Which is a categorical question. And that means we got P right here. Check answers, 100%. Woo! Don't want to make any errors. Let's go find one that has us go through a little more of the process. Here, I'll put a break in the video. Break in the video. Let's go find one that has us do the reject and not reject the null. Now, I'll just say this. We're going to go in a little more detail here. But rejecting and not rejecting the null is when your p-value is lower than alpha. When the p-value is low, reject the null. When the p-value is high, just let it fly. Don't reject the null. So when the p-value is low, reject null. Thank you so much, Cliff. 50 points for positivity in the chat. When the p-value is low, reject the null. When the p-value is high, just let it fly. Are there any in this assignment where we reject the null? Okay, this one right here. Cool, cool. This is a tough one. Let's go do it. Here we go. So here we are, another Stat 1 question. You're welcome, Trace. Excellent work. Ah, I think it'll go well. I hope. Crowns. Yay, crowns. Like, your teeth look fine, Brian. That's because I got temporary crowns on, too. A random poll of 700 working men. So this random poll is going to be a sample size. Let's just go take the data right here. And let's go find out. So a random poll of 700 working men. 700 is going to be the what? Notation, notation, notation. 700 is going to be the what in this problem? 700 is going to be the what? We have to identify each part of this. 700 is going to be the what? And then we've got in that poll 9%. I'll do the next one. So we have to identify all the notation as we go through this. Great job, Elizabeth. That's the sample size. And then this is the sample proportion. Be very careful. This is where notation mistakes happen, is that's p hat right there. So the reason it's p hat is because it's not the truth. It's just what we learned from a sample. So from 700 working men, 9%, because it came from a sample, had taken a second job to help pay bills. That's not the truth. That's just what we learned in a sample. Estimate the true percentage that are taking on a second job by constructing a 95% confidence interval. So we're going to have David M. Lane in the chat right here. I'll write the equation, and we'll see why we're using the David M. Lane. And you might know the answer to the z-score because it's 95% confidence. The David M. Lane website is just where we can go to look up z-scores, but this is kind of a classic confidence interval. These equations are given to you on the test. P hat, which is our sample proportion, plus or minus a z-score, which is going to be the percent confidence we go out on the curve. And then right here we have the standard error, which is p hat times q hat over n square root. Q hat, so what would q hat be right here? So I'll let you take a moment to think about it. If p hat is equal to 0.09, and I'm writing it that way so you can kind of make a good guess right here. Q hat is the complement, and take a moment to think over in the chat what q hat will be equal to, and then we're just needing to find z, and we have everything we need to make this confidence interval. So what would it be right here? What would q hat be? Q hat is the complement, which means it's 1 minus. Very close. Yours might be 8%. So it would be 0.91. Yours might be a little bit different. So excellent work. 20 points in the chat. Great answers. It's just going to be whatever adds up to 100. So the way to do this is 1 minus. If you just do 1 minus 0.09, you will get, oh no, don't worry. Pfft, great work out there. Don't worry. We're just practicing. Only matters when we get to the test. And tests, don't let a test define you. So the z-score is what we need to get now. And we have the David M. Lane in the chat. So if you're wondering where this website is, it's in the chat. And what we need to get is we need to get the z-score for a 95% confidence interval. And you're saying, Brian, we know that. But the way to get z-scores for confidence intervals is to shade the between area. Like this is a 2.5% confidence interval. It covers 2.5% of the curve. No one would ever do that unless you're crazy. This is an 80% confidence interval. And watch the z-score down there. As I get more confident, the z-score is getting bigger. At 95% confidence, you basically have your 68, 95. It's basically 2. Basically, you could use 2 and it's 95.449 if it's 2. So if you were to go to 2, it's 95.449. Well, let me enter that. Then that's 2. But it's 1.96 classic statistics. Computer programs will find out. They'll just find it for you. But a lot of times, I don't know. I just got a huge rant about it. It's 95.449 if it's 2, but Yeah, anyways. So this number right here is the z-score we're looking for. And now we have all the information we need. Remember that z-score, let's mark it right here. Z is equal to 1.96. And that's relative to the percent of curve we are shading in. We're shading the middle 95% of the curve. If we made a 98% confidence interval, it would be wider, 99 even wider, to shade more values on the curve. So the z-score specifically controls for the percent confidence. Now, here's the important thing. We're making a confidence interval. We're going to use it for a test here in a second, and we'll write the test out. So let's do the confidence interval of 0.09 plus or minus 1.96 square root 0.09 times 0.91 over 700. And we'll get the two values right here. So let's go ahead and start solving. 0.09 times 0.91 divided by 700. Don't make an error, Brian. There we go right there. And that's the margin of error. Everything I just solved for right here, punching into the calculator, is the margin of error, which is the plus or minus on the interval. So it's going to go up and down by about 2.1%. So 9% plus or minus 2.1. And let's go ahead and enter that in. See how we're doing on this. And it wants to 3 decimals. So 9% minus this. And that's 6.88. And then 9% plus this. Wow, that's a nice number. And 3 decimals, my Pearson's going to get really mad at us if we don't put in the right amount of decimals. I'm sure someone's done that besides me. So what does this mean? And we'll do the test here next really quickly. What does this mean about the claim of 5%? 5% is not in our interval. So what are you going to do if I'm saying I think it's somewhere between 6.9 and 11.1%? So because 5% right here is not in the interval, we can reject it, as in we have evidence that more than 5% of working men have a job. We have evidence that more than, and we'll look at this here in a second. I think that's got everything correct. Good. A little bit afraid, went a little bit quick there at the end. But let's look at this from the testing standpoint, because that was the big question. To do this exact same problem as a statistical test, we need to ask a little bit different information. Now, we have a hypothesized proportion of 5%. 5% is what we are hypothesizing is true. Let me write it in a different color. So this goes to how do we do the test? We hypothesize, let's not use that color. We hypothesize that 5% is true. We observe 9% in our sample. So now we need to do the statistical test with, right here. We need to go P naught minus, oh my gosh, brain is slowing down today, P hat minus P naught. Yes, over P naught, Q naught, over N square root. We will get a z-score once again. So we would probably want to write our null alternative. We go exact methodology. The null would state that the true proportion is equal to 5% because that's the hypothesized. We're trying to see if there's evidence that the true proportion is greater than 5%. When we do this, because we just rejected the null, the z-score is going to be very large. Sorry, I've got like 3-4 minutes. So let's go ahead and solve this. And we have our sample proportion right here. Minus P0, P naught. P naught times Q naught over N square root. Let's go solve this. And so, oh my gosh, I didn't put in my N. Sample size from earlier was 700. And let's go ahead. P naught times Q naught over N square root. And let's take 0.09 minus 0.05. And the Z, oh my gosh. 4.8. Holy mackerel. Because here's what we do next. And hopefully I can review this later, Elizabeth. I'm going to have to run here in half a second. My appointment's in 23 minutes. When we go and we plot this Z-score, we're asking, what's the probability of getting a Z-score greater than 4.8? And the answer is it's off the scale. So in this instance, our p-value is very, very what? Our p-value here, and we'll draw a visual for it. Our p-value for this problem ended up being very, very what? The p-value would be way over here, and it would look something like this. And what we're saying by this is this value right here is very, very unlikely to observe by random chance, given 5% is true. And because the p-value is so small, what are you going to do to the null hypothesis? And this p-value here is a p of about 0, and that's super small. And guess what we do to the null? We go to the null, and we reject the null, and we have evidence that more than 5% of men have a job, second job. And that's what we found over here when we built the confidence interval for the original question. So the same thing could be done right here. We have evidence that more than... Is this making a little more sense? I have to literally run. Email me. I'll help out more later. Sorry, short office hours today, but let me know. I will be back. But for now... Oh, that's awesome. So that's helping. Bye for now, everyone. Bye! Time for appointments.